really make a difference as to whether or not your function is injective or surjective, right? So if you increase the domain, you increase the likelihood of breaking injectivity. And similarly, if you increase the codomain, you're going to increase the chances that you fail to be surjective as well. So the domain, kind of the important point here is the domain and the codomain are specified and are part of the data of a function. And I said that before, but now hopefully it's really clear why this is important, right? Because the properties that that function has actually change depending on that data. So it's important that you specify that. And it's one of the reasons, again, I think we've all seen this sort of question in your first year calc course or your high school calc course, where it's like, here's a function, find its domain. And that's stupid because functions have domains. You don't find them, right? That doesn't make any sense. You have to say what it is ahead of time. Excuse me. So we're going to expand on this a little bit, and we're going to start to do some proofs with this, okay? So the first thing that I want to do, let's do the following proposition. I'm going to call it a proposition. So propositions, by the way, are just a type of mathematical result, right? So typical mathematical results might be something like theorems. Those are the big famous ones. Propositions are like baby theorems. Then you have like corollaries. Corollaries are usually results which immediately follow from other results. So they're not kind of like standalone results exactly. And then lemmas. And lemmas are the baby results that you use to then prove other things, right? So corollaries are direct results of other results. So they often like follow immediately after a theorem, or lemmas usually immediately precede a theorem because you want to prove something and then use it to help you prove something bigger, right? That's what a lemma is. So those are kind of the things, and propositions are just kind of your generic middle of the road results. Okay. So if F maps B to C and G maps A to B are both injective, then their composition F compose G, and let me just make sure we did that right. G goes A to B, F maps B to C, good. Their composition is also injective. Okay, so I actually want you to take a little bit of time, see if you can do this proof. It should be 1 or 2 lines, right? It shouldn't be terribly long and it's not terribly complicated. And there's only one thing that you can do. That being said, again, if you haven't really ever flexed your proof muscles before, this might seem difficult, and that's okay, but give it a shot. I'm going to give you about 3 minutes here, and I want you to get as far as you can. And don't hesitate to ask questions in the chat though. I'm happy to help out there. If this is your first, foray into proving stuff, and if it is, that's fine, then I think it's important to talk about how you set things up and how you execute, because if you set up the problem correctly and not even do any math, just write down the right things, it can make a big difference in terms of how easy it is to solve the problem, at least in these early days, as our problems are relatively straightforward now, and they'll get harder as we go on later, okay? So let me start by let's kind of think about what the intuition here is. And that can really help by drawing a picture. So our intuition is kind of like follows. In fact, it's going to be hard to see our intuition in the case where things succeed. It might be easier to see our intuition in the case where things fail. But let's draw a picture. Okay, so let's say that this thing here, this is A, this is B, and this is C, right? So we've got G here, and we've got F here, all right? And okay, what could go wrong, right? Again, we need the composition function, F composed with G here. We need this thing to be injective. So what things could go wrong? Well, certainly in G, if 2 things map to the same point, then it doesn't even matter if F is injective, because automatically we're in trouble, right? We've got 2 different things which map to the same thing in F, and then if we carry that forward, under G, if we carry that forward under F, I now have 2 things mapping to the same thing. Boom, the composition isn't injective, right? And that goes wrong as well if F fails to be injective. because even if these two things, even if we can guarantee G always kind of separates points, right? Things map to their own thing. If F fails to be injective, then those two things could map to the same point. And we run into this same problem, right? Where we've got two different things mapping to the same thing. So it's critical here that both F and G end up being injective, right? So we need injectivity in order to guarantee that the composition is injective. So we might kind of just like draw that as, let me move F a little bit higher here. These map to these points. And then these map to their own points as well, right? So if everything's injective, then two different points on the left will always map to two different points on the right. That's an intuition for injectivity that we can use. And if both G and F do that, then certainly when I chain them together, the chain is going to do that, right? The composition. Now, this is a nice bit of intuition, but unfortunately, it actually doesn't help us do the proof at all. Okay, so in terms of doing the proof, let's try that and see what happens. So I want to recommend really, especially in these early days, that you take a second and you spell out exactly what it is that you know and what it is you're trying to show, okay? So we know, and even if you are confident that you know these things in your brain, you should still write them down. You want them in front of you. So we know that F and G are injective. All right, so that is, and don't just write that down. You actually want to know what that means, right? You actually want to put that into words. So we know that for all, let's say A1 and A2 in A, G of A1 equals G of A2 implies that A1 equals A2, right? So that's the definition of G being injective. We'll do the same thing for F. And again, there does eventually become a point where you don't have to do this. But I recommend, especially because even if you've done proofs before, you're relatively new, right? You're relatively new to doing proofs. It's not like you've been doing it as a professional mathematician for years. So we're going to write it out and we're going to unravel the definitions that we have. So these are our assets, right? These are the tools that we have. We've assumed that these things are true, so we can use this. If we ever get to a point where we have G of A1 equals G of A2, boom, immediately we can say A1 is equal to A2. That's part of the power that we've been given. Now, let's figure out what it is that we want to show, right? So we're told that they're both injective. What do we want to show? We want to show that F composed G is injective. So we want to show, some people abbreviate that as just WTS, right? Everyone knows what that means. So I want to show, so for every A1, A2 in A, F of G of A1 equals F of G A2 implies that A1 is equal to A2, right? And again, I think that step is actually critically important. I think a lot of people start to try and prove injectivity in this case without first writing that down. And they're like, wait a second, what is even the domain of F composed G? Oh, it's A. So that's actually what I have to assume is true. I have to assume that F of G A1 is equal to F of G A2, and then prove that A1 is equal to A2, right? Okay, so we need to start here, right? This is what we need to do. We're going to start by assuming that this is true, and then we're going to show that this is true. Okay, and we've only got two tools, these things right here. So this setup doesn't take a terribly long amount of time, but is really, really useful because now you have the tools in front of you, you know what you're trying to do, you know where you need to start, you know where you need to finish, and you know exactly what you can use, right? And in these sorts of setups, with these sorts of problems, having setup there is usually really, really good. So, okay, we are going to start by saying assume that F G A1 is equal to F of G A2, right? That's where I said we were going to start. And again, now the only two, like we're stuck, right? And when you're stuck, you go and you look at your tools and you say, okay, according to my tools, what could I use here? Well, I don't know anything about GA1 being equal to GA2. I don't know that that's true yet, right? But what I do know is that F of G of A1 is equal to F of G of A2, that's actually the second tool there, right? It's written a little bit weird because, you know, in our tools it's written as B1 and B2, but basically I'm thinking of GA1 here as being, that's my B1, and that's my B2, right? So I've got F of B1 is equal to F of B2 here. So that tells me that B1 is equal to B2. So since F is injective, the things inside of the F's must be equal, right? And you can think about injectivity as that. Because F is injective, anytime F of something is equal to F of something else, the things inside the F's are equal. So we get the G of A1 is equal to GA2. And now you're like, oh yeah, clearly the first tool is the thing that we should use, right? Because G is also injective, so the things inside of it must be equal. So since G is injective, A1 is equal to A2, right? And look at what I underlined and said, show this is true. That's what we wanted, right? We started by assuming that the thing in the yellow box, F of A1 is equal to F of G of A2. And we wanted to show that A1 is equal to A2. Well, you know, it's easy to lose the forest for the trees here, but at the end of the day, that's what I've managed to show, right? I showed that A1 is equal to A2, and that's what we wanted. So we're done, right? The composition is also injective like we wanted. Okay, so does that make sense? Are there any questions about what I did there? Okay, and of course, you know, okay, great. Yeah, I'm glad if that makes sense. And this is okay if this like doesn't immediately come to you, because there's lots of people for whom this doesn't. But there is a very real sense that as a mathematician, like who's been doing this for a long time, when I say that there's only one thing you could have done, I don't know if you can all see what I mean by that. Like if you know where to start, right? F of G A1 equals F of G A2, and you need to get A1 to be equal to A2, and these are the two tools you have. There's only one thing you can do to make this proof work, right? Lots of proofs have plenty of different ways that you can approach and attack them, but this one, no, there's only one thing that you can do, right? And this is what I'm saying, especially in the early days of us, and in most first year proofs classes, there's usually is only one thing you can do. It's not until you get into higher years that things start to get a little bit more complicated. Can I explain once more? Sure. So we're going to assume, right, we're starting here because we're trying to prove that F is injective. And when you're trying to prove a function is injective, you're going to assume that, you know, the function at one point is equal to a function at the other point, and then show that their arguments are equal. That's what it means to be injective. So we're going to prove that. And then we just start peeling off the layers like an onion. Okay, so we've got this composition here of two functions. And I can say, like, look, I can take the F out. I can basically strip the F off and say that the things inside of the F are equal. And the reason I can do that is because F is injective, right? And so that's how I get to this thing right here. G of A1 is equal to G of A2. And then the question is, can I strip the G off, right? Can I take the G layer off? And the answer is yes, because G is also injective. So injectivity allows me to kind of like take off those layers and assume that the things inside the function are equal, right? That's what injectivity does for me. So knowing that both of these functions are injective allows me to take off both of the layers to eventually get that their kernel inside is equal. Yeah. Okay, cool. Let's do a different one, a similar one. Some people think this one is actually harder. I actually think this one is easier, but let's see how it goes. Let's also call it a proposition. Why not? So same setup. We're going to have F mapping B to C and G mapping A to B. So if these are two functions such that F compose G is injective, then G is injective. Okay, and then kind of as a bonus here, does F have to be injective? Okay. We should do an equivalence to finish the proof, even if it's obvious, right? Depends on what you mean. Adam, can you like expand on that? Just like you know 1 + 1 = 2, but do you know how to prove 1 + 1 = 2? Yeah, I mean, like, that's starting to get, often the easier the result is, the harder it is to prove, sort of thing. But yeah. Okay, so Adam, if you can clarify what you mean by that, then I can expand on that a little bit more. But let's try this. So let me kind of, while Adam, hopefully you're writing, let me kind of expand on this a bit. So notice how this is different than the previous question. So in the previous question, we assumed that the functions themselves were injective and wanted to show that when we combined them, the combined thing was injective as well. Now we're doing almost kind of the opposite, right? We're assuming that combined they're injective. We don't know anything about the functions themselves individually, but we're assuming that when we combine them, the answer is injective. So now the question is, if we know combined they're injective, I want you to show that the inside function had to have been injective, right? If their composition is injective, then the inside function is also injective. And then as a bonus, does the outside function have to be injective? Okay, so I'm going to give you, 3 to 5 minutes or so to work on that. And again, don't hesitate to throw any questions in the chat if you have any. See, perfect. Okay, so let's see if we got anywhere with this. This is, again, one of these questions that I think more people actually get wrong when you're new with proofs, but I think is actually an easier question once you're comfortable with proofs. And it just goes to show that, like, again, this is, if you've never used these muscles before, it can definitely seem harder, right? So let's see how we do this proof. Okay, and so once again, I don't promise that I'm always going to do this, but I think in the early days, it makes sense to do the setup with you as well, so you can see how to do it. Okay, hold on. I'm going to read those chats in a second, but let me just do the setup. Okay, so what we know. So we know that for all A1, A2, and A, that if f of G A1 equals f of G A2, then A1 is equal to A2, right? This is our only tool. It's the only asset we have. We want to show that for every A1 and A2 in A, G of A1 equals G of A2 implies that A1 equals A2, right? Okay, so I've done the setup. I've just written down what it is I know and what it is I want to show, right? So in terms of what it is I want to show, I'm going to assume that GA1 equals GA2, and then I'm going to prove that A1 is equal to A2. Let me just quickly read the chat. Yes, yeah, I think you basically have it. And then ln x squared is injective, but x squared is not injective. Yeah, we'll come to that in a second because it depends on where the squared is there. Because ln x all squared and is not ln of x squared, right? So we'll hit that in a second. Okay, so we're going to start here. Right, we're going to start by assuming this is true, and then this is what we want. Right, so let's assume that GA1 is equal to GA2. Okay, and now I've hit a roadblock, right? I don't know what else to do next. So again, once I hit a roadblock, what I'm going to do is I'm going to dip into my tool bag and say, what from my tool bag do I know? Okay, well, I know this is true, right? I know that if f of g of a1 is equal to f of g of a2, then a1 is equal to a2, but I don't have any f's here. So what I'm going to do is I'm just going to introduce the f's, right? I'm going to say, like, listen, let's compose with f on both sides. So composing with f, we'll then get f of g of a1 is equal to f of g of a2, right? And there's no magic there. like you know that GA1 and GA2 are equal. So if you plug them into the function, they're going to give you the same thing. And this is actually kind of more or less what Adam was talking about, which is if you know that two things are equal, right? This is that like converse direction. If two things are equal, when you plug them into the function, you get the same thing out, right? That's what it means for a function to be well-defined. So we're not doing any magic here. You're definitely allowed to do this. And now we can use that tool that we have underlined in blue. I know that these two things are equal, so A1 is equal to A2. And since F composed G is injective, A1 is equal to A2. And that's what we wanted. Voila. Okay. So again, I hope that you can see like this is actually a shorter proof, right? It actually took less work in order to do this one, but it's a little bit weird because it's not direct. Like I wasn't just, peeling off the layers like I did in the previous case. Like I had to do a little bit, I don't want to say a trick, but I had to be like, oh, I need to introduce something here in order to be able to use the tool that I have, right? So yeah, well, yeah, exactly. So let's think about this because again, we're kind of getting, I think it's easy to lose the forest for the trees. Have I proved that G is injective? Well, what did I do? I assumed that G of A1 is equal to G of A2. And then a whole bunch of stuff happened in between. And if we want, we can black box it. We can say, okay, let's not worry about what that stuff is in between. Whatever I did in between, I ultimately finished with the fact that A1 is equal to A2. Right? And from that's what it means for G to be injective. I started with G of A1 being equal to G of A2 and finished with the arguments being equal. And that's exactly what it means to be injective, right? So like I said, it's easy to get lost in the intermediate steps, but hopefully you can see that from where I started and where I finished, that's precisely what it means for G to be injective, okay? Could we have also proved by contrapositive? So you actually want to say that if A1 is not equal to A2, then the G of A1 is not equal to G of A2? Let's see if that's going to work. Okay, so you might be able to go that way. The only thing I kind of want to warn you about is usually, so not equal sign do not behave as nicely as equal signs, right? Equal signs are very strong. And so when you say that two things are equal, you're saying a lot about them. When you say that two things are not equal, you don't have a lot of power. So I believe that there is, and that you could prove this using the contrapositive and saying that two things are not equal. But you have to be a little bit careful about your reasoning and your logic. Often, as a mathematician, we often say that those proofs are much less aesthetically appealing because being able to say two things are equal is much nicer than saying that they're not equal. And you have to be a lot more careful about the logic. Even if it seems easier, you have to be careful about the logic because again, not equal signs. For example, not equals are not transitive, right? So we know for equal signs, if A is equal to B and B is equal to C, then A is equal to C, right? You have transitivity of the equal sign, but you don't have transitivity of the not equal sign, right? If A is not equal to B and B is not equal to C, A could be equal to C, right? So you have to be really careful about using not equal sign, but it doesn't mean it couldn't be done. But I would say that you lose some aesthetic appeal, okay? And because GA1 equals GA2 turned out to be true, then we're going to assume that F is injective as well. Oh, okay. So I started by assuming that G of A1 was equal to G of A2. That doesn't guarantee that F is injective because for F to be injective, I need to show that no matter what, if I start with F of B1 is equal to F of B2, then I always get out B1 is equal to B2, right? It would be like me saying, assume that B1 is equal to B2. Well, it turns out F of B1 is equal to F of B2. That doesn't prove injectivity because I assumed that the arguments were equal to begin with, right? If I want to show that F is injective, I'd need to start by assuming F of B1 is equal to F of B2. And then from that show that B1 was equal to B2, right? Can we prove that F is injective first, then G is injective next? Maybe, except G is not or like F does not have to be injective. Doesn't G need to be surjective in order for F to be injective? No, I would say. I don't think it does. Okay, does anyone, so I've kind of told you the answer to the bonus question. I've said listen, it does not need to be injective, right? F doesn't need to be injective. Does anyone have a counterexample, an example where F is not injective, but the composition of F and G is? If F is injective, does that mean G is injective automatically? It does not. But you know what? I love these questions. First of all, let me begin by saying the following. This is phenomenal. I love that you're all just kind of immediately taking what we've proven and twisting it and trying to see like what other things you can get out of it. That's super cool. I love that. Ultimately, what my goal is though, is that when you ask these questions, you're able to answer them for yourselves, right? Like I know, and I love it. And I don't want you to ever stop asking me questions. But the ultimate goal here is that in a couple of months, you're going to ask these questions and your first instinct will actually be to try it yourself and only come to me once you're not actually certain whether you're right or wrong, right? But I love it. Like I said, don't stop asking me questions, but eventually I'm going to start turning this on you. I'm going to say, well, what do you think? Okay. So, okay. Now, was anyone able to answer the bonus? Does anyone have a counterexample? An example where F is not injective, but their composition is? Do we need to prove F is not injective by contradiction? Well, you don't know. F could be injective. So the point here is not that F is guaranteed not to be injective. It's that you don't know anything about F. Okay, F could be injective. It might not be injective. So G is x cubed, F is x squared. Their composition. Okay, so Nicole, that's an interesting idea. Domains are really going to matter here though, right? Domains and codomains. There might be a way of making this work, but you really have to, because their composition is going to be x to the power of 6, right? Which is probably not injective unless you restrict the domain enough, right? Because with x to the power of 6, you get the same issues as x squared, right? Where negative numbers and positive numbers will map to the same thing. So if you can be a little bit more precise about the domains, you might be able to make that one work out. Yeah, it's not saying that that's wrong, but don't forget you have to include domain and codomain. Okay, here, let me give you an example. Let's try not to, as a general rule, when you're trying to construct examples and counterexamples, always try and do the easiest thing you can. Okay, I think, okay, but Adam, that composition is not injective, right? F composed G in that case is equal to -1 because your outside function is the constant function, right? The constant function is definitely not injective. Many things map to the same thing, right? So it's an interesting idea, but it doesn't work just because your outside function is constant. If F and G are constructed in a way that F's domain doesn't include G's codomain, well, then you just can't compose them. And I would say that's not okay. Like you've kind of just cheated and said, look, these are two functions that I can't even compose in the first place. So then I can't even say that F composed G is injective because you just couldn't compose them, right? So it's an interesting idea to try and like technical loophole the question, but it's not, I would say it's not a valid counterexample because you don't have that F composed G is injective because you just can't compose them in the first place. Okay, so here, let me try and give you an example. And you'll notice I keep going back to the same function. So let's take something, let's take f of x. Well, no, we're gonna always specify domain and codomain. So I think I'm just gonna do r to r here. And you know what, it's possible for me to make a mistake. So everyone just kind of, double check me to make sure I'm not crazy here. Okay. So I'm going to take these two functions and I claim that if I compose these, I'm going to get an injective function out. And you might be upset. You know what? Actually, let me make the output here r just so that we don't have any complaints about the codomain of G not being the domain of F. And if we compose them, what do we get? We are going to get just x, right? And this function, I'll check the chat in a second. This function is injective, right? You all agree. And the function G is injective as well, right? The square root function is injective. I mean, maybe you haven't proven that. And if you'd like to, that's a great exercise. It's not too hard. But the composition of these two functions is injective. But the function f, as we talked about last time, right, is definitely not an injective map. So here we have an example of a composition being injective, but f is not an injective map. It could be, right? So for example, if I changed f so that its domain, if I changed f and g, so that the domain of f was 0, infinity, then f actually would be an injective function. And we would get that their composition is injective. But here, it doesn't matter. If I let f map r to r and be x squared, it is not an injective map. And let's think about what happened here. The bad values, right? The things which make f fail to be injective were just never seen because G prohibited that, right? The square root of x always maps to a positive number or a non-negative number, but it never sees the negative numbers. So the part of f that failed to be injective just never got hit. It's like if we want to draw this as a picture, right? So let's say this is, A, B, C, and let's say we know that, f is a badly behaved function, right? So it does something like it maps these two, sets to the same thing. Forgive my terrible drawing, but so it's not injective, right? Because it takes these two things and maps them into the same thing. But when I look at what G does, G only maps into this thing here, right? Oh man, somebody turned their mic on by accident and now I can hear myself. Okay, perfect. Thank you. So does that kind of make sense? Do you see like f, even though f fails to be injective because it maps two things to the same thing, but after I do the composition, that second part, that bad part of f just is never seen, right? And that's why the composition can be injective even though f fails to be. Let me go through the chat here, just make sure I got everything. So for this question, we're only assuming that f composed G is injective, not f is injective. That's correct. Absolutely. We're only assuming that the composition is injective. F should fail to be injective on values G, not a surjective function, does not take. Right, exactly. Yeah, Alexander, perfect, exactly. And that's exactly what I've tried to draw here. So you probably put that in before I drew it, but absolutely that's exactly my point. It fails to be injective on values that G does not assume as part of its image, and therefore the composition is injective. Perfect. But wouldn't the composites function domain be restricted from 0 to infinity, which would make the function f injective as well? No, so this is interesting. Like, you're right in the sense that when I've composed them, it's almost as if I've restricted the domain to 0 infinity of f, right? Really, like that's almost like what's going on, but it doesn't change the fact that f has a bigger domain, right? Yes, when you do f composed G, f never ends up seeing this, like f composed G never ends up seeing that bottom part, but it doesn't change the fact that the function f is still defined on the bigger domain, right? This is why it's so important that we specify domains and codomains, right? We really have to, because you would say, listen, if I restricted the domain of f to be 0 infinity, it wouldn't make any difference to the composition. And I would say you're absolutely right. And in that case, f would be injective. But that's a different function, right? That's a different function f. So you can't, you're not allowed to get away with that. So you have to be very careful and very technical and very precise about the things that we say. And that's an important lesson, about mathematics. Okay. What's the requirement for two functions to be composite? So in order to compose two functions, you just need to, no problem. You just need that the codomain of the inside function is the domain of the outside function. And really, you don't even need that. You just need that the codomain of the inside function is a subset of the domain of the second function, right? That's the only thing you really need. Okay. So let's see, what do we need to do? Okay, we're going to do, because I think, we're going to use this. We're going to do one more about injective, surjective, and then we're going to start talking about cardinalities. And so, for the record, everyone, like this isn't a course about injective and surjective functions. They will come up, okay? But this isn't necessarily, what analysis is going to be like. I'm just trying to get us to cardinality, countability, because we'll use those words. And so I need you to know what things mean when they're countable or uncountable or whatever the case might be. And then we're going to go into analysis proper, right? So if you're like itching for analysis and you're like, where is the analysis? Don't worry, it's coming. Okay, it's coming. And when it comes, you'll probably be like, no, I'm sorry, I didn't actually want this. But we'll worry about that when we get there. So let me give you one more problem. This one's a little bit tricky. Will we ever get into number theory? No. Number theory is very different. There is something called analytic number theory. Analytic number theory is brutal, right? It's very, very hard. So there is an analytic number theory, but that's not here. But Math 102 will get into number theory, as will 202 if you're interested. And then eventually there's 315, which is a third year number theory course. Those are number theory courses if you want to take them, but yeah, we're not going to have any here. Here is something that is worth saying though. Nothing that we've done here is outside of the scope of 102, right? So for those of you who are maybe here and you're just like, oh man, this is crazy. Like clearly 157 is brutal. We're still doing Math 102 stuff. Okay, so this is Math 102 in like week 5 or week 6 or something like that, but it's still Math 102 stuff. So we're not actually in the realm of crazy yet. We'll get there though, I promise. Don't worry. Okay, proposition. So this is probably the hardest one. It's not hard, but I think if you don't know how to think about functions, and I think I'm still trying to get you guys to think about functions. You see how I've been writing the functions up here as kind of like as two sets, and then it's almost like a factory machine, right? Like it eats something in its domain and outputs something in its codomain. And that's how you should be thinking about functions. Don't think about functions in terms of their graphs, okay? There will be plenty of opportunity for that later, but the graph is a useful mechanism for studying functions, but it's not how you should think of a function, okay? A function is always eats an input, creates an output, and that's how you need to think about functions. Okay, so here's my proposition. If f, or maybe let's use g to be consistent. So if g maps a, what do I want to say? Suppose g mapping a to b is a function. And we're going to do bad grammar here because I'm going to start a sentence with then, but you're allowed to do that in math. Then g is injective. If and only if there exists a function, let's call it h, from b to a, such that h compose g is the identity function on a, okay? And so here the identity function is the one that doesn't do anything, right? Okay, so the identity map is just, right, exactly, perfect, thank you, Victor. The identity map is just the map which you give me an input and it just reproduces the output, right? So this is, and this is definitely worth stating, so this is the statement here that G has a left inverse. Right? Because that's what it means to be invertible, right? If you think about what the definition of an inverse function is, it's such that if you compose it with the function, right? So G and G inverse, when you compose them, you get out the identity function, right? That's what the inverse does. Now, we're not saying that G compose H is also the identity, because that's not going to be true in general. But we're saying that if you compose it so that H is on the left and G is on the right, you will get the identity. So it's a left inverse, not a right inverse, but it's a left inverse. Okay, so you are injective if and only if you are left invertible. Maybe we could write that as a comment. So a function is invertible if and only if, is, let's say, injective here. Is injective if and only if it is left invertible. Okay, so that's basically what this comment is. All right. So what I want us to do is, today is our 2-hour class, I think, right? So let's take a 10-minute break. And then I'm also going to give you 5 minutes to work on this problem. Okay. So we're going to take a 15-minute break. We'll come back at around 10:15 and we'll take up this problem. So you get an opportunity to stretch, get some coffee, whatever your case might be. Now, as a heads up, this is an if and only if. So there's two things you got to prove here. The converse direction is the much easier of these directions. Okay, so assuming that H composed G is the identity, implies that G is injective, is the easier direction because hint, hint, we already basically proved it, right? It's the previous example, right? So figure out how to prove that with one line, or you can prove it from scratch by imitating the proof that we just did. And if you want to do that, phenomenal. The forward direction is a little bit more complicated. If you try and think about a function in terms of a graph, it's impossible. But if you think about a function in the way that I've drawn up here, then it becomes much easier. Okay, but you have to think about a function in that way in order to be able to do it. You have to construct the left inverse. Okay, so that's your job. Okay, so let's break up. 10 minutes for a break, 5 minutes to work on this question. I will be around even if my chat goes off. I'm going to refill my coffee, but I'll come back and answer the chat. Let's say 15 minutes. I spent a couple of minutes blabbering, so I'm going to say 10:18 by my watch, but that's 15 minutes starting now. Okay, so we'll come back. Like I said, throw any questions in the chat if you have them. I'm happy to answer that. People could see this. Okay, so in terms of inverse, this is kind of an aside as a, maybe we're a little bit rusty and we should talk about what an inverse is, and I'm totally happy to do that. So one of the problems that occurs when you talk about an inverse is inverse with respect to what? So let's be clear about that. So let me, we're going to tangent a little bit here and we'll talk about something slightly different than injective and surjective functions. We'll come back to this in a second. So when you have a binary operation, okay, so binary operation is just anything that eats two of something and produces something else. So for example, addition is a binary operation, right? Because it eats two numbers and produces one out, right? Multiplication is a binary operator because it eats two numbers and produces one out. Function composition is also a binary operator. It eats two functions and gives you one function back out. Okay, so these are binary operators. Now, an identity for a binary operator does the following. So whatever your operator is, if you do, let me just call what do I want to, I'm just going to use this to indicate the binary operator because, we don't know whether there's going to be addition, multiplication, function composition. This kind of conversation holds in general. The identity operator satisfies the following. Okay, so the identity is the thing that when you act it through your binary operator on any other element, nothing changes. Does that kind of make sense? So somebody tell me, what is the identity for addition? So for addition, the identity, I'm going to call that ID plus. 0, exactly. Okay, for multiplication, 1, exactly. And then for function composition, well, unsurprisingly, it's the function, it's the thing I just mentioned, right? It's the map which just sends X to itself. And so for function composition, we have that the identity map, I'm going to use that little circle there of X is just equal to X. Okay, and you can check that. That's why that's called the identity map. You can see that no matter what side, and it's important that this actually works on both sides as well. Okay, so the identity, not only you have X with the identity is equal to X, but also the identity with X is equal to X. Okay, so the identity works on both sides. So this identity function, if you compose it with F. So if you do the identity composed with F, you just get F out. And if you do F composed with the identity, you still get F out, right? That's why this is called the identity map or the identity function. And then you have an inverse, okay? So the inverse of X is, let's call it X inverse like that. Or maybe let's call it X inverse satisfies X binary operator X inverse is equal to the identity. Okay, so the inverse, if you give me a fixed number X, the inverse of that is such that when you combine them with the binary operator, you get back the identity. Okay, so for addition, what is the inverse of a number? Okay, so we know that, right, it's the negative of it, right? Exactly. Because if you take X and you add it to negative X, you get back the additive identity, which is 0, right? X plus negative X is equal to 0. What is it for multiplication? Yeah, it's exactly. It's reciprocal. It's 1 over X, right? Okay. And so here, for example, is our first indication that the inverse doesn't always exist. Right? Because, for example, exactly, we know that 0 does not have an inverse, right? So you're not guaranteed that inverses always exist. And for function composition, I'm just going to call it function here instead of function composition. The inverse is the inverse function, right? Yeah, exactly. It's F inverse, which, like, we don't have a nice way of kind of expressing it, but right, that's what the inverse is. So X, let me call it F inverse is the inverse thing, right? So what this means is that F inverse composed with F has to be the identity, and F composed with F inverse has to be the identity, okay? So by definition, the inverse map must work on both sides, okay? And that's, that wasn't crazy with addition or multiplication. You're like, yeah, I know that these two things are commutative anyway, in the sense that the order of addition doesn't matter and the order of multiplication doesn't matter, so we didn't care about it. But function composition, the order of composition does matter, right? We know that that's true. And the identity by definition must work on both sides, okay? So that's what an inverse is. When we say inverse, we mean it has to work on both sides. How do you define a function again? I mean, for that, the true definition of a function is in the formative thing, and you should go to that. I don't want to rehash the entire, left total, blah, 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 blah thing. But otherwise, it's just a map from one set to another, which is well defined, okay? Now, up here, what we're saying is we're not saying that H is an inverse, okay? Because we can't be guaranteed that it works on both sides. But what we're saying is a left inverse, right? That it works if you put it on the left side only. And so this is kind of like, this is a weaker thing, but it's still, you can imagine this is still useful to know, right? And in fact, the fact that this is an if and only if means that this is equivalent to being injective. Being injective is the same thing as being left invertible or having a left inverse, right? So that is a cool way of actually thinking about injective functions. Okay, all right, so now we are at that point where maybe let me take it up. Like I said, the previous direction is the most simple. It's so much so that I'm not going to do it. Okay, because the answer is literally just look at the previous example above. The identity map is injective, so you know the inside function is objective and you're done. Right, exactly. And or if you want to actually repeat the previous example that we did, and the proof is word for word verbatim, where we assume that F composed G was injective, but now assume that F composed G is the identity map, and even easier, the fact that A1 equals A2 will fall out. Okay, so if you want to repeat that proof and give it a shot, and this time under the stronger condition that not only is H composed G injective, but it's actually the identity map, you'll see the proof is actually easier. Okay, so I'm going to leave that for you. So this is the more interesting direction. And the way that I like to do this is I think it really, really helps to visualize what it is that you're doing in terms of setting up the inverse function. Okay, so let's just think about what G does. Okay, so here's my function G. And I'm going to draw a couple points over here. I'm going to draw a couple points over here. So these points are actually the elements of the set. Okay, so the big circles are the sets, and then the points inside of it are the actual elements. So because this is a function, everything on the left has to have an arrow coming out of it, right? And I'm going to assume it's injective, so no two arrows can point at the same thing, right? That's what it means to be injective. The arrows can't point to the same thing. So maybe they cross over like this and do something like that. That's an injective map, right? Could you outline what we're assuming? Oh yeah, you're absolutely right. You know what? I didn't do that. I did not do that. And I said I would. So you're absolutely correct. Maybe let me move this down here. Okay, so in this direction, we're going to assume that the function is injective. So we know that G is injective, right? So G of X, let's use A1. G of A1 equals G of A2 implies A1 equals A2. What we want to construct H from B to A such that H composed with G is the identity map. Okay, thank you for that reminder. You're right, I was definitely being a little bit bad there. Okay, but we fixed that. Okay, so this part, this is just intuition, okay? So this is not part of the proof. You would not include this. This is just intuition. Somehow these arrows became white. I definitely didn't want them to be white. And I hope that I remember where I sent them. I think that's what I did, right? Okay. So this is the function G. G does this. All right. So what we want to do is we want to define the function H. H is going to go back the other way, right? And let's just think about what it needs to do. So if I take G first and then come back on H, and I'm going to draw the H arrows in blue. So if I follow the yellow arrow first, and then I follow the blue arrow back, I have to start, or I have to finish where I started, right? Does that make sense? Right? That's the statement right here. So if I follow G first, the yellow arrows, and then I follow the H arrows back, then I have to start or finish exactly where I started. So that's very nice because that immediately tells us that this is how these have to be defined, right? We're going to invert the arrows. So the blue arrows, anytime it makes sense and there's a yellow arrow pointing towards something at B, what am I going to do? I'm just going to reverse it and point it in the other direction. But this fellow here doesn't have any arrows pointing at him. But to be a function defined on the set B, the function has to be defined for every element in B. So the question is, what do I do with this thing? Where do I send it? What do I map it to? Exactly. Yeah, Divyansh, perfect. The answer is we can do literally anything that we want with it because it doesn't matter, right? Let me show you why it doesn't matter. So maybe I'll, what color is this? Red? Maybe I'll map this thing. I know that the picture is getting a little bit busy because there's a bunch of stuff going here, but hopefully you're following along. The point is that we can do anything we want with it because the only thing that we have to satisfy is that if you follow a yellow arrow and then come back on a blue arrow, then you finish where you started. Nothing ever hits this point, right? There's no yellow arrows going to it. So we don't care where it goes. It can go to literally any place that it wants to go, and we'll still satisfy H composed G being the identity, right? So what we're going to do is we're just going to choose some element on the left-hand side and send everything that doesn't have a yellow arrow pointing to it. We're just going to send it all to that. This isn't the only way you could define it. There are other ways you could as well, which just shows that left inverses are generally not unique, but whatever. Okay, so here's the proof proper. So I'm going to assume that the sets are not empty, because if they're empty, this is dumb. So fix some element A naught in A. Okay, this is the thing that I'm going to map everything else to. If it doesn't have a yellow arrow pointing to it, then it's going to go to A naught. So we're going to define H from B to A as H of B is equal to A if G, not using F, and A naught otherwise. Okay, so this is, you're going to have to think about this a little bit, but this right here is exactly me saying, if it has an arrow pointing to it, just the blue arrow is sending it back, right? Just reverse the arrow. So it says, if you give me an element on the right-hand side in the B set, then you're going to map it to A if G of A is equal to B, right? Again, there's a little bit of stuff to parse there. You're going to have to think about it a bit, but that's what this is saying. You're just going to reverse the arrow as appropriate, okay? And then the second part, A naught otherwise, says if there's no arrow pointing to it, then you're going to map it to A naught, right? i.e. anything on the right-hand side that doesn't have an arrow pointing to it is going to have an arrow pointing towards A naught when we define the inverse function. Now, why is this a function? Right? The thing I've circled in blue, you can't do in general. Why can we do it here? Exactly, since G is injective. So you need to check, I'm going to leave this for you. Why is this not scrolling? Okay, so check that H is well defined, right? That it actually defines a function. Exactly, Chloe. So you're right. We want to show that this is well defined, that it's actually a function. And the reason it's a function is because it is injective. And this, again, kind of goes back to what Adam was talking about, which that somehow injectivity is the converse of being well defined here. So when I define the inverse map, I'm basically going to use injectivity in reverse, right? And that is the reason why. But hopefully you all believe it, right? Because it's one-to-one, there's only one arrow that can go back the other direction. And then it's a simple matter to check that, if you give me any A, so I get H of G of A. And if you look at the definition of H, you say, well, listen, if the thing that you gave me is G of A for something, then you just map that back to A, right? So H composed G is the identity. All right, so there's something to check there. I've left the well-definedness for you because I think that's a good exercise. I don't think it's hard. I think, though, that there's a little bit of definition unraveling. So it's a good exercise for you. But check that you understand why, if you're an injective function, this inverse thing is actually well-defined and makes sense. And you'll notice this inverse here is not injective, right? Like the inverse here generally is not injective. And not only was it not injective, it's not unique, right? There were many ways that we could have defined this inverse function. We could have mapped, where it says A naught otherwise, we could have mapped that to a different point, A naught. We could have mapped them to several points, right? We could have spread them out if we wanted to. So in general, there's actually a lot of different left inverses for an injective function, right? That's why we only say this is a left inverse, not the left inverse, because it's not unique. A true inverse, by the way, in the context of this discussion up here, an inverse, a true inverse, is unique. You can prove that it's unique, okay? So if you want, that's kind of a nice little bonus thing that you could try as well. The proof is very straightforward. It's one line, but prove that if an inverse exists, say for function composition, then that inverse has to be unique. Okay, are there any questions about that? So again, if you're typing, just keep typing. But let me say the following. So you've probably noticed that all of today I've been talking about injective functions. And of course, we know that there is another concept, surjectivity, right, which says that your range is actually your codomain. Now, injectivity and surjectivity, so true inverses only exist for functions that are also surjective. Mahmoud, yes, exactly, right? True inverse. Oh, actually, you know what? That statement segues perfectly into what I'm about to say. So every single one of these statements has a corresponding analog for surjective maps, okay? So where was our first thing? Let me scroll up here. Okay. So this thing, the composition of injective maps is also injective. This is true for surjective functions as well. That's an exercise for you to prove, okay? I'm going to assume that we know it, but I'm going to leave that as an exercise for you to try on your own. It's kind of like a MIDI homework thing, okay? Prove that the composition of surjective functions is surjective. Now for this one, if the composition is injective, then the inside function is injective. The thing about surjectivity is it's often dual, which means that the result doesn't hold exactly. It often holds with a small twist. If you want to change this result to surjectivity, then it goes like this. If F composed G is surjective, then F is surjective. Okay? So when we talk about surjectivity of the composition function, that guarantees that the outside function is surjective, not the inside, right? Hopefully you can see this duality. The results aren't exactly the same. There's kind of like this dual, okay? So I want you to try that as well. It's this statement, but change all the words injective to surjective, and instead of G being surjective, it's F that you want. And then this thing right here, can anyone guess? Like if you had to guess what the corresponding dual for this is, remember, if G is injective, if and only if it's left invertible, what's the natural kind of dual to this? So G is surjective if and only if what? If you had to guess. It's right invertible. Yeah, exactly, right? So it's going to be surjective if and only if it's right invertible. And I suggest that you try proving that as well. And now this really ties in nicely. Yeah, investable, I like it. This ties in nicely with Mahmoud's statement, which is you are true inverse if and only if you're both injective and surjective. But that makes sense because if you're injective, you have a left inverse. If you're surjective, you have a right inverse. And so if you're injective and surjective, you have both a left, exactly, you're bijective. And so you have a left and right inverse. And those actually, you can prove that they have to be the same thing. If you have a left inverse and a right inverse, then they're actually unique and they are the same function, right? And so this is kind of a cool thing that we can do. Is H injective in this case? H is actually surjective in this case. Yeah, the inverse of like the left inverse of an injective function will be right. Okay, so this brings up a great question, and I got it in the direct message, but this is actually a phenomenal question. So I said that the corresponding analog of this proposition here is that a function G is surjective, a function H is surjective if and only if it has a right inverse G, right? But what you'll notice is in this statement, that G has a left inverse, H. H has a right inverse G, right? And that means that H is surjective, right? Does that make sense? So like the left inverse of a function is the right inverse of its inverse, right? If we look at H composed G is equal to the identity, H is a left inverse for G, but G is a right inverse for H. So this, theorem states that G is injective, but then correspondingly by our dual statement, that also means that H has to be surjective. And if you look at our proof, you can kind of see that that's true, right? Like because G had to always have an arrow coming out of it for everything on the left-hand side, by virtue of how we've constructed H, there's an arrow pointing to everything in A, right? And that's the definition of surjectivity, right? Everything in A has at least one arrow pointing to it. So you can see in the proof here that H is going to be surjective, right? So there's this kind of like cool thing where injectivity and surjectivity are dual. And now I am going to ask you to put on, the grown-up mathematician hat a little bit, in that I'm not going to state these and I'm not going to prove these for you. Okay, so I'm going to expect you to go through them and state them and prove them yourself. And of course, if you've forgotten, you can ask and you can be like, hey, I don't remember what the statement of that theorem was, and throw it on Piazza or something and I'll help you out. But I do expect you to figure out what the correct statements are of these, of these 3 examples that we did, but for surjectivity, and then to prove them on your own. Okay, so that's, really good practice, really good practice. Okay, so are there any questions about that? Otherwise, I'm going to pivot a little bit. We're still talking about injective and surjective functions. Did I define bijective the other day? I know that it was brought up. Somebody talked about bijectivity, but did I actually define it? I didn't define it? Okay. So definition, a function f from A to B is bijective if it is both injective and surjective. Okay, so for those of you who are wondering, like, you kind of heard this word bijective being bandied about, and you're like, I don't know what that means. Yeah, bijective is just a fancy way of saying both injective and surjective. Okay, and proposition. Again, I'm not going to prove this because it's an immediate result once you've proven the corresponding analogs for surjectivity. A function f from A to B is bijective if and only if f is invertible, and not left invertible, not right invertible, truly invertible, has a 2-sided inverse. Okay. My A is a little weird there. Let me try and fix it. Okay. So I'm going to leave that for you. Again, there's nothing to prove here. In fact, we probably could have called this a corollary, because once we know the statement about surjectivity, this is immediate, right? Because if you're injective and surjective, you have a left and a right inverse, and then it's a simple matter to prove that those are the same thing. But give it a shot, see what you can do. And if you get stuck, that's totally fine. You're allowed to get stuck. Just ask me questions. I'm happy to go through them with you. Okay. Now, the reason why bijective functions are some of the most important things you can study in math. Right? They come up absolutely everywhere. And the reason that they come up absolutely everywhere is we often in mathematics are interested in figuring out when 2 things are the same, right? Secretly the same. So A to B is injective and B to A is injective. Yes, actually that's true. Yeah, that's a great point. So both the map and its inverse end up being injective. So yeah, that's absolutely cool. In fact, the fact that this is tying on something important, but I'm going to bring it up a little bit later. So I actually don't want to dive into it now, but you're actually hitting, you've hit the head on the nail on the head about something really cool that's about to happen. So yeah, good point. So the reason why bijective functions are useful is because they tell us when 2 things are the same, but often they kind of are the same in disguise, but they're the same nonetheless. The first lesson that we get on how bijectivity tells us things are the same is counting, okay? So you may have realized that injective functions tell you something about the size of a set, right? So let me ask you the following question. So here we're going to kind of pivot, and this is going to be, let's just call this cardinality. Okay, let me ask you the following. Can I define an injective map from a set with 3 elements to a set with 2 elements? Okay, is that possible? Can I define an injective map? Okay, you all say no, why not? Like, give me some sort of heuristic. If you actually know the name of the principle, which allows you to do this, you can say it, but why can't I? Okay, yeah, okay. Pigeonhole. Okay, so pigeonhole is the correct principle. You won't be able to map every element in the domain. I mean, I can map every element in the domain. It's just that they won't be able to map to a unique thing, right? There's not enough elements in set B to map from set A. Yeah, sure, absolutely. So, and this is the mathematical principle that this is the pigeonhole principle, right? I've got three things on the left, and they all have to, in order to be injective, they all have to map to something different on the right. But the right only has two things in it, right? And it's impossible for me to map three things uniquely to two things. And the reason for that is called the pigeonhole principle, right? One of those things has to have two arrows pointing towards it. So that's not possible. So this is interesting, right? Because it immediately tells us that if our sets are finite, then, and I have an injective map from A to B, then A must have fewer things in it than B does, right? No, right? So this suggests that if A and B are finite sets, and there is an injection F from A to B, then A has at most as many things, or at least, sorry, right? No, at most. Right? A would be less than or equal to B, so it has at most B things in it. Does that make sense? Do you all agree? Like if there's an injective map, A should have fewer things in it, right? Now that works if it's finite, but this leads to the notion of cardinality. So cardinality is the idea of let's count the number of elements in a set. And in the case of finite things, you're like, yeah, that's kind of like obvious. You know, I could just count them. But here we go, definition. The cardinality of a set. Let's give the set a name. S is the number of elements in S, denoted like the absolute value of S. Some people use a different notation, but this is fairly standard. And if there is an injection from S to T, then we say that S, the cardinality of S is less than or equal to the cardinality of T. If two sets are infinite, can we compare their size or use a trick with injectivity to compare them? A great question. And this is really what we're building up to, because comparing the size of finite sets is relatively trivial, right? In theory, you could just count the elements of S, count the elements of T, and figure out which one is bigger. The real thing that we want to do is figure out for infinite sets, can we compare them? So that is absolutely what we're building up to. Yeah, so nice foresight to kind of see what we're going for. Okay. So if there's an injection from S to C, we're going to say that the cardinality of S is less than the cardinality of T. In the case of finite sets, we can convince ourselves that this is obviously true, but this definition does not say that S is finite, right? S is any set. So right now, that definition is somewhat formal because we're saying that even if there's an injection from an infinite set to another infinite set, then we're still going to say the cardinality of S is less than or equal to the cardinality of T, okay? And, oh man, am I going to prove Cantor, Bernstein, Schroder? I probably don't want to. Yeah, and okay, let me give you another definition before I kind of go further. So definition. So a set S is countable if its cardinality is less than or equal to that of n. Okay. You have to be careful because induction will only let you make finite comparisons. Induction actually doesn't let you make infinite comparisons. So this is an interesting thing. It is possible there's something called transfinite induction, but that's a more complicated thing. And in fact, in order to talk about transfinite induction, you already need infinite ordinals. So like, we don't want to get too far ahead of ourselves, but you know, it's an interesting idea to use induction, but strictly speaking, induction is usually for finite things. Okay, so here's an important thing. A set is countable if its cardinality is less than or equal to that of the naturals, i.e. if there's an injection from that set into the natural numbers. And again, this is 102 stuff. I'm not telling you anything that's crazy here. Again, it's maybe like week 6 or 7 of 102, but this is the general thing. Okay, so we're not doing anything here that is too crazy yet. So that's what it means for a set to be countable. In fact, my definition here is going to disagree with 102. 102 is a set is countable if its cardinality is equal to that of the natural numbers, and that's nonsense. Literally nobody else in the math world says that that's true. Math 102 uses their own notation there. I have no idea why, but this is the real world definition of what it means to be countable. So you're either the same cardinality as the naturals, or you have less than or equal to cardinality. Okay. And then, so we're also going to say, I guess I should add this in here, definition. Two sets S and T are said to have the same cardinality if there is a bijection, or maybe let me write that down notationally. Is a bijection from S to T. Okay, so the reason why bijections are important for us is they tell us basically when two sets have the same number of elements, right? Because as we were talking about above, okay, I'm going to scroll back down to this, don't worry, but I'm going to scroll up quickly. So in our conversation up here where we said, can I define an injective map from a set of 3 elements to a set of 2 elements? The answer was no. But certainly we could define an injective or a surjective map, right? For a bijection, this number of elements in S and the number of elements in T, or in this conversation in A and B, has to be the same. Do you all agree? For me to find a map which is both injective and surjective, A and B have to have exactly the same number of elements, right? Because for the same thing, an injection, you need to have less than or equal to number of elements in B, but for a surjection, I have to have greater than or equal to number of elements, right? And so the only way for both of those things to be true at the same time is that if I'm both injective and surjective, i.e. I'm bijective. So bijective sets have to have exactly the same number of elements in them. So this allows me to compare the cardinalities of 2 different sets, right? Everyone's okay with that? Now, I'm not going to prove this theorem. If anyone's really interested, I'll give you all a handout with this. So this is the Cantor Bernstein Schroder theorem. And it's going to sound obvious. The proof is very hard. So if S and T are 2 sets, then this is true. Okay. And again, if you're looking at this from the idea of like them being numbers, in the case of finite sets, this is obvious, right? You're like, yeah, if A is less than B and B is less than A has to be equal to B. This is that entire like anti-symmetric thing in the formative handout, right? But that's not what this is saying, right? Like, think about it. The fact that the cardinality of S is less than or equal to the cardinality of T is the statement that there is an injective map from S to T, right? And then the fact that the cardinality of T is less than or equal to the cardinality of S is the same as that there's an injective map from T to S. So another way of stating the Cantor and Bernstein Schroder theorem is if there's an injection from S to T and an injection from T to S, then there is a bijection from S to T. And the important thing there is that the two injections that you use don't have to be inverses of one another. Okay, so that's kind of the important and critical thing. So when S is smaller than T, there's always an injection between them. Yes. Yeah. Because you can make it, right? Like in the case where there's finite number of elements, what you do is in S, you would just enumerate them. You'd say like S1, S2, S3, S4, and eventually you'd stop at like S7 or something. And then in T, you would say T1, T2, dot, 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 through T10. And then you would just map S1 to T1, S2 to T2, S3 to T3. And eventually you would create an injective mapping, right? But yeah, absolutely. If S is smaller than T, there's always an injection between them. So the power of Cantor, Bernstein, Schroder is if you can show that there is an injective map from S to T and an injective map from T to S, then they have to be the same cardinality. Exactly. You only need two injections to prove the existence of a bijection. Okay. And the two injections that you choose, you might say like, well, obviously if they're equal, there's a bijection. And if I can find that, then this theorem is dumb. The point of this theorem is you don't have to find the bijection. If you can prove that there's an injection in either direction, the theorem guarantees for you a bijection exists without constructing it, right? You just know that one exists. So this is crazy important. This is super useful stuff. Okay. So again, if anyone's interested in the proof of that, I can do a thing. It does use only elementary techniques, but the proof is involved. It's not a straightforward proof at all. Right. And it's very clever. There's a reason it's a named theorem. Generally, if a theorem has a name on it, it's because, it's brilliant. But you can do things with Cantor, Bernstein, Schroder. Let me just very quickly like show you a bunch of crazy things. Okay, so maybe let's do an example here. So what do I want to say? So define So let's take this to be the even naturals. All right, so weird things happen with infinite sets. The even naturals are the same size as the naturals. Right? And your first instinct to this is, no, wait a second. The even naturals are a strict subset, right? Like there are less even naturals than there are natural numbers. No, there are exactly the same amount. And this is because this is the sort of funky thing that happens when you start to deal with infinite sets. Can anyone tell me what the bijection is? Don't even use Cantor, Bernstein, Schroder. What is the bijection? Anyone? Yep. I'm going to use n here just because I think it's a little bit, right? Yeah, there it is, right? There's the bijection. It absolutely works. You can check. I'm going to let you all do this on your own. This is bijective, right? It's injective, it's surjective, or alternatively, if you want, you could define the inverse map, and that would prove the bijection as well. Normally, of course, you can't, guarantee. Well, let me just say, like you would just the inverse map is to divide by 2. And normally you can't divide integers or natural numbers by 2 and expect to get a natural number. But because they're all even, you're guaranteed that that's possible, right? So there it is. Here's the thing, which intuitively is going to hurt your brain, but you're like, oh no, but the bijection is actually really easy. All right, here's another one. So by this, I mean the interval 0, 1 in the real numbers. So the interval 0, 1 has the same cardinality as the real numbers. Anyone have a bijection for me? You might have to think about this one a little bit. Anyone? Here, I'll give it to you. I'm going to let you check it. Okay. Interesting. Okay. So is that gonna work? That might work, actually. So Anika, that I like that one. Try that one. Jenjen, yeah, I think yours is basically just the inverse of mine, right? Yeah, there's lots of them, right? So go ahead and kind of work on that. But I think you all have kind of the right idea, right? Which is we know there are functions that can do this, right? That map the entire real line into the open interval 0, 1. This is the one I like. I like using arctan. Some of you have some nice ones too, though. It looks like you've chosen some rational ones. You've chosen some logarithms. Give it a shot, okay? Make sure that you can prove that your ones are actually bijections and see if you can make that work, okay? So this is the one I chose. Before we end here, let's do the following. So just take a guess. Maybe you know. It would be cool if you did, but. So I want you to tell me whether we should put this in. So for the following, okay, why is my things aren't reacting the way I want? Okay, so does everyone know what n and z are, right? N are the positive whole numbers, right? 1, 2, 3, 4, 5, 6, blah, blah, blah. And the integers are all the whole numbers, right? So negative numbers, 0, and positive numbers. Okay, sweet, yeah, all right. Those are equal, okay? See if you can prove it. Okay, this Q thing are the rationals, so they're the collection of fractions, right? Whole number fractions, 1/2, 2/3, 7/5, all that. Okay, nice, I like it. You guys are doing very well. Okay, these are actually equal. And this is a crazy thing, right? Because it seems like there are way more rational numbers than there are naturals, but actually there are the same amount. Okay, yeah, this is strictly not equal. Right? The reals are strictly bigger. They are a bigger infinity. So immediately we know there are infinitely many naturals, there are infinitely many reals, and we are guaranteed now that there are at least two different infinities. Let me ask you though, is there one in between here? Is there an infinite cardinal? Infinite cardinal between n and r? It's not an open problem. We know the answer. But you're on to something. So what do you all think? If you had to guess, is there an infinite cardinal between the naturals and the reals? We know definitively what the answer is. Okay, we've got a no. Anyone agree or anyone disagree? Maybe there's any yeses. Everyone's just too afraid to say. Okay, good. A yes. I am glad there's a dissenting voice. Got some yeses. Lots of yes question marks though, right? Really uncertain. No question marks. Perfect. Maybe. I like it. So maybe is more or less the correct answer. The answer is whether or not there is one Yeah, whether or not there is one is independent of Zermelo-Fraenkel with choice, i.e. the current set of mathematics that we have all agreed is true. We don't know whether there is one, in the sense that you cannot prove it exists, you cannot prove it doesn't exist. It is independent of mathematics. Whether or not there's a cardinality between the natural numbers and the real numbers is an axiom that you have to take. You either have to assume that there is one, or you have to assume that there isn't one. And depending on which assumption you make, completely changes all of the mathematics that you've invented. Now, most mathematics does not hinge on whether there is a cardinality in between these two numbers. But the point is, you have to take this as an axiom, whether it's there or not. And if you assume, this is called CH. If you assume CH, i.e. you assume there's no cardinality in there, if you assume CH, then you get a completely different brand of mathematics than if you assume not CH, right? And this is crazy, because if you think about this, you're like, wait a second, the naturals, I understand. The reals, I understand. How do we not know if there's anything in between there? And the answer is, yeah, that is completely and totally independent of mathematics. You have to add it as an axiom to your theory of mathematics, right? And so that's a crazy thing. So if anyone wants to look up a little bit more about this, this is called the Continuum Hypothesis. Mathematicians are split. Like mathematicians, what most mathematicians will do is prove the result both with CH and not CH. And like for most mathematicians, it doesn't matter. 99.9999999% of the mathematics you do will not depend on whether you assume CH or not CH. For those who do assume CH and not CH, they usually prove both results. So they assume CH, prove the result, assume not CH and prove the result, and tell you what the two different results are, so that when you're in the CH universe, you know what thing to take. And when you're in the not CH universe, you know what thing to take. Okay. I promise you nothing in 157 will use CH. You will never need to know whether the continuum hypothesis is true or not for anything in this course. But if you do want to check it out, the continuum hypothesis is the thing to throw into Wikipedia. And you'll go into a deep dive of things you probably won't understand, but like of really, really cool stuff. And the fact that this is independent of ZFC. Okay. Yeah. All right, everyone. So that's going to finish it for today. It'll take me a little bit to get the recording up, just because it takes a while to process, especially like a 2-hour video. But it'll probably be up in the next hour or so. That's going to finish it off today, though. So our next lecture is going to be on Thursday, and I'll see you then. Thanks, everyone, for coming. Do we have pre-class readings? No, I don't. No, I don't think there's anything that you need to read unless you really want to. I would say, Mo, like if you want to, do the surjective exercises, and then if you want, try and prove these cardinality equalities and inequalities. And if you want, that can be your like reading, right? Is to see if you can do those. When is the first assignment? I'll post the first assignment tomorrow. Good question. Do we have any assignments or problems before the next class? No, there's nothing to do before the next class. But again, like, if you want to practice, practice. There's lots of homework problems that I gave you. Are you? Yeah, I mean, usually people drop, but I mean, maybe you all are just having such a good time. What about the Cantor Bernstein? Yeah, let me make one. I don't have one ready, but I can make one. I only have the bare outline of the proof in my brain, so it's not even something I could reproduce on the fly. So I'm gonna have to read it and then make a handout for it, but give me a second. I'll try and do it today and or tomorrow, but you might have to bug me about it on Thursday if I haven't gotten it done yet. Yes, I think so. And if nothing else, if any of you choose not to continue on in this course, which again is fine, but you'll have gotten an exposure to these ideas before 102, and they should really help you if you choose to go take 102. Like I said, this is like week 5, 6 of Math 102. So, you've already kind of got a nice head start there. Yeah, absolutely. Cantor, Bernstein, Schroder is in the 102 notes. I think Shai has proven it there, so you can use that as a handout if you want. I think his proof is okay as well. Like, I don't think that there's an obvious improvement other than the fact that I might be able to give it a little bit more intuition behind why it works. But Shai's proof of this is fine in the 102 notes. Yeah. Is there proof for n equals q? There is. I think it really helps to know that countable unions of countable sets are countable. But basically what you do, the proof for proving the rationals or the naturals is you take each fraction and you map it to the pair of the numerator and denominator, and then you can show that Z cross N is countable, and then you're done, right? So that's basically how that proof goes. I mean, I wouldn't try and find the bijection. That's really something you want to do Cantor, Bernstein, Schroder for. Could you quickly explain N is less than R? That probably not. That proof takes a long time and is quite hard. So I will do it. I will do it in class. I'll probably do it on Thursday. But that is the Cantor diagonalization argument. So if you want to get a little bit of a head start to see why those two things are not equal, you want Cantor's diagonalization proof. And it's a beautiful proof. It's super clever. It's super awesome. It's also super intuitive, but the first time you read it, you might be a little bit confused. So you might want to wait until Thursday, but I will bring it up and I'll do it with us. I mean, no, you don't know. Pi could, in theory, you could construct, basically you assume for the sake of contradiction that there is a bijection, that it is possible to enumerate every real number. And then you construct a real number, which is not in your list, which is a contradiction because you said that you listed them all, right? So that's the key point. No, because R is definitely not countable, right? Like, so there won't be a diagonalization proof for the countability of R, but there is one for the uncountability of R. Yeah. But yeah, here's how the proof goes. Just very quickly, if you want to try and adapt it, assume that R is countable. Okay, so assume that you can write down and list every real number and write them down, right? Be like, this is the first one, this is the second one, this is the third one. And then based off of that list, see if you can construct a real number which is not in the list, right? And that would be a contradiction because you said you wrote down all the real numbers, but then you were able to write down a real number you didn't write down, right? And that breaks math. That's how the proof goes.